The air in Death Valley on the afternoon of July 10th, 1913, was not moving. That is the first thing to understand about it. The basin sits below sea level, walled on every side by ranges of dark rock that climb several thousand feet. And in the middle of summer, that geometry becomes something close to a closed system, a place where the ordinary exchanges between ground and sky and wind that cool most landscapes simply do not occur the way they do anywhere else. Hot air descending from above compresses as it falls, and in compressing it heats further, and when it reaches the floor of a valley, this narrow and this deep, there is nowhere for that heat to go. The rock itself, dark and dense, and oriented to catch the sun from the moment it clears the eastern ridgeline until the moment it drops behind the western one, does not merely warm under that light. It stores it, and then it gives it back upward through the hours when there is no sun, so that a person standing on the floor of the valley in the middle of the afternoon would feel heat arriving not only from above, but from below, pressing from both directions at once, the ground under their feet radiating as though the stone had its own internal source. That afternoon, at a weather station called Greenland Ranch, in the northern part of the valley, a thermometer recorded a temperature of 134 degrees Fahrenheit. The reading would be examined and re-examined by meteorologists for the rest of the century and into the next one. The station records were checked. The instrument calibration history was reviewed. The surrounding physical conditions, the basin geometry, the descending adiabatic air, the dark rock surface, the absence of any cooling wind were studied as a system, and each element was found to be consistent with the number the thermometer had shown. That number, 134 degrees Fahrenheit, remains the highest reliably measured air temperature ever recorded at the surface of the Earth. Not the temperature of the ground, which can run considerably higher, but the temperature of the air itself, the shimmering column of it sitting at instrument height above the valley floor, the air a person would be breathing. The valley at that hour would have been, in the most precise physical sense, an oven. The term is not rhetorical. A conventional household oven set to bake at moderate heat runs somewhere in the range of 325 to 350 degrees Fahrenheit, and the floor of Death Valley that day was considerably cooler than that. But the mechanism is not so different. A bounded enclosure with dark walls that absorb energy and release it back into the interior, with limited circulation, with the heat arriving from multiple directions at once. The adiabatic compression of descending air, which is the process by which air heats as it is forced downward, and squeezed by the increasing pressure of the atmosphere above, was doing in that valley what a heating element does in a closed box, adding energy to air that had nowhere to escape. The walls of the valley held it in, the floor gave it back, and the thermometer at Greenland Ranch, sitting in its white-painted instrument shelter a few feet above the ground, simply measured what was already there. There is a particular quality to the silence of Death Valley in high summer. The absence of wind in the basin is not merely meteorological. The walls that prevent cooling air from entering also prevent the random eddies and gusts that in most landscapes carry sound across the ground in unpredictable currents. The valley floor absorbs that variability. What remains is a heat so uniform and so total that it presses on the senses not as a single thing, but as a condition, the way darkness is a condition rather than an event. The rock and the air and the sky above are all participating in the same process, storing and radiating and compressing and holding still. And at the center of all of it, on the afternoon in question, the thermometer needle was resting against a number that no surface weather instrument on Earth, as far as all available records show, has ever reached again. 7,000 miles away, in a direction roughly opposite south and east, deep into the Antarctic interior, the Earth was doing something entirely different with heat. At Vostok Station, a Soviet research outpost sitting at an elevation of nearly 12,000 feet on the East Antarctic ice sheet, scientists had been measuring surface air temperatures since 1957. The station was established during the International Geophysical Year, and it occupied one of the most thermally extreme positions on the planet's surface, not simply because Antarctica is cold, but because of what 12,000 feet of elevation does to the physics of heat loss. At that altitude, the atmosphere above is thin enough that infrared radiation escapes into space with very little resistance. On a still, clear night, the ice sheet radiates heat outward and receives almost nothing back. The temperature falls and keeps falling. On the night of July 21st, 1983, the instrument at Vostok recorded a surface air temperature of negative 128, 6 degrees Fahrenheit, the coldest naturally occurring temperature ever directly measured by a surface weather instrument anywhere on Earth. The conditions that produced it had been building for days, the kind of deep stillness that settles over the Antarctic plateau in the heart of winter when the sun has been absent for months and the surface has been losing heat continuously without interruption. Clear skies, no wind, the dark ice sheet radiating outward into a sky that was offering nothing back. The cold sank and pooled and continued deepening until the thermometer reached a number that, like the one in Death Valley 60 years earlier, has remained at the edge of what instruments have since recorded. At negative 128, 6 degrees Fahrenheit, the physical character of cold begins to exhibit properties that do not have easy everyday analogies. The air at Vostok at that temperature would be so dry that moisture from a breath would crystallize almost immediately, the water vapor turning directly to ice without passing through the liquid state. This is a process called deposition, and in conditions cold enough and dry enough, it happens fast enough to be heard, a faint crackling sound in the immediate vicinity of the face, as the moisture in exhaled breath freezes before it has dispersed. Researchers who have worked at Vostok and other deep Antarctic stations have described this phenomenon informally as the whisper of frost, the brief sound that breath makes when the air is cold enough to turn it solid before it travels more than a few inches. The silence around the station in July is otherwise total. The plateau stretches flat in every direction for hundreds of miles. There is no wildlife, no vegetation, no running water, no wind on the coldest nights. There is only the ice and the dark and the temperature falling toward numbers that have no common reference point. The elevation of Vostok is itself a significant part of why the cold reaches what it reaches there. At sea level in Antarctica, the atmosphere is thick enough to absorb some of the outgoing radiation from the surface and radiate a small portion of it back down, a modest insulating effect. At 12,000 feet, that insulation is substantially reduced. The ice sheet sits up in the atmosphere where the radiative pathway to space is shorter and less obstructed, and on still, clear nights, the surface simply pours its remaining heat outward and receives very little in return. It is the same geometry that makes mountaintops cold, accelerated by the particular combination of Antarctic winter, extreme dryness, and the complete absence of cloud cover that the high interior plateau produces when conditions are calm. The record at Vostok is not an accident of a single unusual night. It is what happens when all the components of a system that removes heat from a surface are working together at their maximum. The Earth, then, holds both extremes, its hottest measured air temperature above a desert basin below sea level, its coldest above a continental ice sheet above 12,000 feet, and both are produced by the same basic principle operating in opposite directions. Geometry constraining air movement, driving temperature toward one edge or the other, while the planet as a whole turns slowly, and the sun rises and sets across both poles and both deserts, indifferent to the numbers the instruments are recording. What NASA satellite measurements added to this picture, beginning in 2003, was a category separate from air temperature, land surface temperature, the actual heat of the ground, rather than the air above it. Air temperature is measured in an instrument shelter, a standard distance above the surface, which means it captures the temperature of the air in a specific small volume. Surface temperature is different. It is the temperature of the thing the sunlight is landing on directly, the rock, the soil, the mineral crust, the sand. In 2003, NASA began a systematic global survey of land surface temperatures using thermal imaging from the Terra and Aqua satellites. And over the following years, the data began identifying one location repeatedly as the hottest surface on Earth. The Lut Desert in southeastern Iran, called the Dasht Alut, is a large plateau of dark mineral crust and stone. It sits in a region of Iran that receives almost no cloud cover through the summer months, and its surface is composed partly of dark-toned salts and minerals that absorb solar radiation with unusual efficiency. In 2005, during the peak of an analysis covering the period from 2003 to 2009, the satellite data recorded a land surface temperature of 159.3 degrees Fahrenheit over a section of the Dasht Alut. Cheshire, not the air temperature, the surface itself, the mineral crust under direct sunlight in a sky that had not seen clouds in weeks. This is the highest land surface temperature ever formally measured on Earth in the satellite era. The Lut Desert is remote enough that it had been studied relatively little before the satellite surveys brought attention to it. It sits in a region with essentially no permanent settlement at its core. The aridity too extreme and the summers too hot for habitation without significant infrastructure. The dark crust that drives the surface temperatures to their recorded extreme is a feature of the desert's specific mineralogy, salts and clays deposited over geological time, eroded and concentrated by the rare events of water movement that occasionally cross the plateau, and left behind as the water evaporated. That surface, dark and dry, and under a sky almost permanently clear, acts in the same basic way the rock in Death Valley acts, but without the shading and cooling that even a single cloud would provide, and with a mineral composition optimized, by geology rather than design, to absorb as much of what the sun sends down as possible. The number the satellite recorded, 159.3 degrees Fahrenheit, sits about 25 degrees above the Death Valley air temperature record from 1913. The gap between them is partly a difference in what is being measured, partly a function of the fact that dark mineral surfaces under direct sun heat considerably faster and hotter than the air immediately above them. Standing on that surface at noon in July would mean standing on something whose temperature was close to that of a cup of freshly brewed coffee, the ground itself functioning as a heat source. The sky above the Lut on such a day would be a hard, unvarying blue, and the horizon would be perfectly flat and perfectly still, and nothing in any direction would be moving. Both the Death Valley record and the Lut Desert measurements are products of specific geographical and atmospheric configurations, and understanding what produces extreme temperatures at one end of the range also helps clarify what produces them at the other. Temperature inversions are among the most direct demonstrations of how geography and atmospheric physics collaborate to trap and concentrate either heat or cold. In a standard atmosphere, temperature decreases with altitude. The higher you go, the colder it gets. An inversion reverses this. A layer of warm air settles above a pool of cold air near the surface, acting as a lid, preventing the cold air from mixing with the warmer air above and rising away. The inversion holds the cold in place. This is most familiar in valleys. On a clear, still night, the surface of a valley floor radiates heat rapidly outward, and the air immediately above it cools. Cold air is denser than warm air, and dense air sinks and flows downhill, pooling in the lowest part of whatever basin or depression is available, the same way water finds its level in a landscape. The valley walls prevent the cold air from flowing out. By morning, the temperature at the valley floor may be 10, 20, or in extreme enclosed basins, 30 or more degrees colder than the temperature on the slope, 50 feet above it. The slope is not warmer because it is receiving more heat. It is warmer because the cold air has drained away from it, downward into the basin below, like something poured. This mechanism contributes directly to cold temperature records in enclosed basins around the world, including some of the most extreme cold readings taken outside Antarctica. Valleys and depressions that combine good drainage geometry, clear skies, minimal wind, and a surrounding landscape that promotes rapid radiative cooling can accumulate cold air over successive clear nights until the temperature in the lowest part of the basin drops to levels that seem inconsistent with the surrounding region's climate. A hillside town half a mile away and several hundred feet higher will wake to a mild morning. The valley floor will be in a deep freeze, the cold pooled there overnight, exactly as the physics of density and gravity would predict, and the inversion above held it in place until the morning sun began to erode it from below. On still winter mornings, when a frost has settled overnight, the most delicate evidence of this pooling can be found in the frost itself, which is not distributed uniformly but follows the contours of the terrain, thickest at the lowest point of every depression, thinning as the ground rises even a few feet. A field with a shallow central low point will frost most heavily at that center, the cold having arrived there first and deepest, the ice crystals accumulating over the hours of darkness into a heavier, more settled layer than the ice on the surrounding slightly higher ground. The cold finds its own level and marks the landscape accordingly, writing the terrain's lowest points in frost each morning, erasing them as the sun climbs. In the Arctic, temperature inversions and the pools of cold air they produce contribute to a phenomenon that sits at the far edge of what weather can make from water: frost flowers. The conditions that produce them are specific enough that they occur only in a narrow overlap of circumstances. Newly formed sea ice, which has not yet thickened to the point where it insulates the water beneath it thoroughly, still allows a small but measurable amount of heat and moisture to migrate upward from the relatively warmer ocean water below through the ice's pores and imperfections. When the air above is cold enough, roughly negative 22 degrees Fahrenheit or below, and when the atmosphere is calm and dry, that upward migrating moisture encounters air so cold that it freezes immediately on contact with any available surface. If the surface is the ice itself, the moisture deposits as frost. But under precisely the right conditions, the frost does not simply coat the surface, it builds upward. The structures that form are called frost flowers. Each one grows from a nucleating point on the sea ice surface, and as the moisture continues to move upward and freeze, the crystal lattice extends, branching and dividing in the same way that snowflakes branch, following the hexagonal geometry of water ice's molecular structure. The result is a small upright crystal structure, sometimes an inch or more in height, with a delicate, branching, petal-like shape that under a clear polar sky catches the light from any angle and returns it as a faint sparkle. A field of frost flowers covers the sea ice surface in what looks from any distance like a layer of white lace, each individual flower separated from the next by bare ice, the overall pattern so regular that it has a textile quality, something woven rather than grown. The flowers are also chemically slightly saline. As the moisture migrates upward through the sea ice, it carries dissolved salts with it, and those salts become incorporated into the crystal structure as it forms. This gives frost flowers a slightly different optical quality from pure ice, a milkier interior, a less perfectly transparent structure, and it makes them chemically significant in ways that sea ice researchers have studied carefully. The salt content of frost flowers contributes to the salinity of the boundary layer between the ice and the atmosphere above it, and that boundary chemistry matters for the aerosol chemistry of the Arctic atmosphere, for the sea ice ecosystem, and for the exchange of gases between the frozen ocean surface and the polar air above. A field of frost flowers is not simply a visual event, it is an active chemical interface, but the flowers exist only as long as the conditions that made them persist. The temperature must remain below approximately negative 22 degrees Fahrenheit. The air must remain calm. The sky must remain clear enough that the frost flowers are not buried under snowfall. The combination of requirements is tight enough that frost flowers are a relatively rare sight, even in the Arctic, limited to specific seasons, specific ice conditions, and specific stretches of weather. Their window of existence is narrow. They appear when everything is precisely right, and they persist only as long as everything stays precisely right. A single gust of wind would end them, not weaken them, not partially damage the field. A gust strong enough to carry a handful of powder snow across the surface would be strong enough to break the frost flowers at their bases, sweeping the entire field of delicate crystals away in seconds, leaving behind only the bare sea ice they grew from, as though they had never been there. The same surface moisture, the same temperatures, the same calm, clear conditions, all the components that produce the flowers, would still be present after such a gust, but the flowers themselves would be gone, and the process of building them back up from the bare ice surface would take time the conditions might not allow. There is something worth sitting with in that fragility. Not fragility as a metaphor, but as a precise physical description of the relationship between a structure and the conditions that produced it. Frost flowers exist because a specific number of independent atmospheric variables are simultaneously within specific narrow ranges: the ice thickness, the ice surface temperature, the air temperature, the air humidity, the wind speed, the sky clarity. Change any one of them past a threshold, and the flowers either cannot form or cannot survive. The fact that they form at all is a consequence of those ranges converging at the same place and time. The fact that they persist is a consequence of those ranges holding still while the flowers grow. The Arctic in winter contains many things built on exactly that kind of conditional precision, formations and processes and exchanges that are invisible until the conditions align and that vanish again when the alignment shifts. The frost flowers are simply one of the most visually explicit expressions of it, the most immediately readable demonstration that a complex structure can exist because a set of independent physical constraints are all simultaneously satisfied, and that the structure's continuation depends entirely on those constraints continuing to hold. When a gust of wind arrives from a direction the conditions had not prepared for, the flowers are gone in an instant that requires no announcement and leaves no visible evidence. The ice they grew from is smooth. The air above it is cold and dry, and still again, and the whole field, every intricate lattice, every branching crystal, every inch of delicate ice lace that took the night to build, has simply returned to the atmosphere from which it was assembled. The ground at Death Valley, radiating upward in the darkness, the ice at Vostok, radiating outward under a winter sky, as black and empty as any sky on Earth, the mineral crust of the Lut Desert, absorbing the morning light, the way stone takes in warmth, the cold air pooling in valley depressions on still nights and marking their geometry in frost. All of these are the same planet, running the same physical laws in the same direction, each one simply occupying a different corner of the range those laws permit. The range is wider than most people picture. The extremes exist at specific places and specific hours, produced by specific combinations of geography and atmosphere that, under the right conditions, push the numbers on the instruments to places they have rarely or never reached again. The frost flowers on the sea ice are somewhere near the delicate end of that range, a structure that requires everything to cooperate rather than simply one or two conditions to be extreme. And there is something restful in that, in the image of an Arctic night, perfectly still, perfectly clear. The surface of the young sea ice, slowly exhaling its moisture upward through the cold, the crystals building in the dark one molecule at a time, the whole field of them growing through the hours of darkness in complete silence, complete calm, under a sky whose stars are reflected faintly in the glittering surfaces of the flowers below. Every flower in that field exists because the conditions have been holding precisely, and the question of how long they will hold is one the flowers cannot answer. They simply grow for as long as the particular stillness lasts, in the precise and temporary space that the cold and the calm and the dry polar air have opened for them, and then they are still. The number on the screen was 54,000, not miles, not altitude, degrees Fahrenheit. The temperature inside a lightning channel at the moment of the stroke, measured by spectroscopic analysis of the light the channel emits in the fraction of a second before it collapses. For roughly 0.2 of a second, a column of air no wider than a human thumb reaches a temperature approximately 5 times hotter than the surface of the sun. Then it is gone. The shock wave it leaves behind is what rolls across the landscape as thunder, and by the time that sound arrives, the air that caused it has already cooled back to ordinary sky. It helps to hold that duration in mind before anything else. 0.2 of a second, the time it takes to blink, unhurriedly, once. In that interval, the air in the channel has been superheated to a temperature that no surface on Earth naturally reaches, that the sun itself only reaches at its outer layer, and then the channel collapses, and the light expands outward, and the nearest tree shudders slightly from the pressure wave before the sound catches up. What the eye records as a flash is the after image of something that had already ended before the image even reached the brain to be processed. The lightning was never really there long enough to be seen. What people see is what it left. That column of ionized air, the channel itself, is the beginning of a much larger picture, because lightning is not only what happens between a cloud and the ground. It is not only the stroke visible from a window during a storm, or the count of seconds before the thunder confirms the distance. The electrical activity of a large thunderstorm extends far above the cloud tops into regions of the atmosphere that most people have no occasion to think about, where events happen at scales and speeds that make the bolt at ground level look like a small local thing. Consider the altitude. An ordinary thunderstorm reaches to perhaps 40,000 feet, its anvil top spreading outward at the boundary where the troposphere ends and the air becomes too thin and warm to allow the cloud to rise further. That upper boundary, the tropopause, is where most people imagine the storm ends. But the electrical system of the storm does not end at the cloud top. It continues upward, through the stratosphere, through the mesosphere, into the lower reaches of the ionosphere, where the atmosphere has thinned to the point that it behaves less like a gas and more like a plasma. In that upper zone, at altitudes between 40 and 80 miles above the storm itself, events occur that were not documented until 1989, when a researcher at the University of Minnesota captured one accidentally. The researcher had been running a low light sensitivity test on a camera system pointed at the night sky above a distant storm, not looking for anything in particular. What appeared on the recording was a brief reddish shape above the cloud tops, not lightning in the ordinary sense, not a channel or a bolt, but a diffuse, structured glow lasting only a few milliseconds. It bloomed and vanished. The shape, when examined frame by frame, was roughly that of a jellyfish, a central brightening with hanging tendrils extending downward, the whole thing spanning tens of miles of sky in the time it takes to blink. The researcher reported what the camera had caught. It took several years, further observations, and dedicated high-altitude camera systems before the phenomenon was confirmed as real, categorized, and given a name. They are called sprites. The name was chosen partly for its informality, as a placeholder during early research, and it stayed because no more formal term gained wide acceptance. What a sprite represents, in physical terms, is an electrical discharge, driven not by charge separation within the cloud, but by the quasi-electrostatic field that a strong lightning strike at cloud level sends propagating upward through the mesosphere. When that field reaches sufficient strength at the right altitude, and the conditions must be precisely right, the lightning strike must be powerful. The strike must be of a particular polarity. The upper atmosphere must be quiet. The mesosphere discharges in that reddish glow, and for a few milliseconds, the sky above the storm is briefly lit in a way that the people inside the storm and the people watching from the ground cannot see at all. The sprites occur above the visible part of the event. The storm produces them and remains entirely unaware, which is not a metaphor for anything, but simply a description of what happens. The reddish color comes from the nitrogen molecules in the mesosphere, which emit light in those wavelengths when they are excited by the electrical discharge. The lower tendrils of a sprite sometimes shade toward blue, because the air density at that level allows for slightly different molecular interactions. The whole structure is faint enough that it is invisible to the naked eye from the ground, which is why aircraft pilots who fly above storms occasionally reported unexplained lights above cloud tops for decades before the cameras confirmed what those lights were. The reports had been there in aviation records for a long time. They simply had not been connected to a known phenomenon because no known phenomenon fit them. Sprites are the most visually distinctive of the upper atmosphere electrical events, but they are not the only ones. A different category was documented around the same period through a different instrument, and its shape could not be more different from the jellyfish structure of the sprite. Where a sprite is concentrated and structured, an elve, the singular is as odd as the plural, is a ring, a flat, expanding halo of dim light that forms at roughly 60 miles altitude and propagates outward from a central point at nearly the speed of light, reaching a diameter of up to 300 miles before fading below the threshold of detection. The whole event, expansion included, lasts about 1 millisecond. A sprite at least occupies a few frames of high-speed video. An elf happens too fast to be seen in any useful sense, and is known primarily from the electromagnetic signatures it leaves in instrument records and from the occasional extremely high-speed camera system that catches its expanding edge. What produces an alphas is the electromagnetic pulse that a powerful lightning stroke radiates upward. The lightning happens, and the electromagnetic wave it generates spreads outward in all directions, including upward into the ionosphere. When that wave reaches the ionosphere, it excites the electrons in that layer, and those excited electrons briefly illuminate the ring-shaped region that the expanding pulse front has reached at any given instant, which is why the ELF appears as a ring rather than a disk, the ring marking the leading edge of the pulse as it expands through the ionospheric layer. By the time the ring has reached 300 miles in diameter, the pulse has passed through and the electrons have settled again, and the sky at 60 miles altitude is dark and quiet and electrically indistinguishable from what it was before the lightning happened, 1 millisecond earlier. Both sprites and elves exist because of lightning, but they occur in conditions and at altitudes so removed from the visible storm that they constitute, in a practical sense, a separate weather system happening above the one people can observe. The thunderstorm is, in this sense, a machine that produces visible events at cloud level and invisible events above the cloud, and the two systems run in parallel, one observable from the ground during any ordinary storm watch, and one requiring specialized equipment at high altitude to detect it all. The ground-level lightning is remarkable enough on its own terms, without needing the upper atmosphere as context. But even at ground level, there are aspects of lightning that most people do not picture when they think of a storm. The way lightning is most commonly imagined is as a bolt descending from cloud to ground, the cloud charged and the ground neutral, the flash moving downward. This is a reasonable description of what the eye sees, but it is not entirely what happens. In a typical cloud-to-ground lightning event, a stepped leader, an invisible filament of ionized air, extends downward from the cloud in discrete steps, pausing for a fraction of a millisecond between each extension, branching as it goes, probing downward through the air until it reaches within striking distance of the ground. At that point, return strokes may rise from high points on the surface, trees, buildings, elevated terrain, and when one of these upward streamers connects with the descending leader, the channel is completed. What then appears as a downward flash is actually the return stroke traveling upward along the completed channel, from ground to cloud at a significant fraction of the speed of light. The bright flash that looks like it came down came up. This reversal, the visible light traveling in the opposite direction from what intuition suggests, is simply a feature of how the channel completes and how the return stroke propagates, and it has been confirmed by high-speed photography. At ordinary frame rates, the distinction is invisible. The flash appears to descend because the stepped leader established the path in that direction, and the eye traces the channel in the direction of its origin. Tall structures complicate this picture further. A very tall building or tower, once a storm system is close enough, can become a source of upward propagating lightning, a leader rising from the structure rather than descending from the cloud, traveling up to meet a charge region above. The Empire State Building, which stands at just over 1,450 feet above street level, with its antenna, is struck roughly 20 to 25 times per year, and a meaningful portion of those events are upward propagating rather than downward. The building sends the leader up, the cloud receives it. This is not a property of the building's engineering or any intentional design feature. It is simply the result of the structure's height, which reduces the distance between its uppermost point and the charge region in the cloud base to a range at which the upward leader can bridge the gap. Any sufficiently tall point in a sufficiently electric field will tend to generate leaders in this way. The Empire State Building happens to be both tall enough and located in a region with a storm climate active enough to produce this outcome reliably across a given year. A lightning rod on a farmhouse does something structurally similar at a much more modest scale. It provides a local high point from which a streamer can rise to meet a descending leader, completing the channel at a chosen location rather than wherever the geometry might otherwise dictate. What these numbers suggest when laid side by side is something about the constant electrical activity of the atmosphere as a whole. The Empire State Building's 20 to 25 strikes per year is a localized figure from a single structure in a single city. Globally, the atmosphere sustains approximately 40 to 50 lightning strikes per second, which amounts to somewhere around 1.4 billion strikes per year across the entire planet. At any given moment, there are roughly 2,000 thunderstorms active simultaneously across the Earth's surface. The electrical activity that produces sprites 60 miles above the mesosphere and upward leaders from tall towers in Manhattan is happening right now in some part of the sky continuously as a normal condition of the planet's atmospheric system. That scale can be hard to hold. It helps to anchor it somewhere specific. There is a river in Venezuela called the Catambo. It runs through the lowlands of the Zulia state in the northwest of the country, fed by the slopes of the Andes and the Sierra de Perijá, and it empties into Lake Maracaibo, a large coastal lake connected to the Gulf of Venezuela by a narrow strait. The geography of this place, the warm lake surface, the surrounding mountains, the particular way the trade winds interact with the topography as night falls, creates conditions that for up to 160 nights per year produce near-continuous lightning storms over the river's mouth. The storms arrive in the evening. They do not move through and pass the way most storm systems do. They settle over the delta of the Catatumbo where it meets the lake, fed by a moisture cycle that the lake itself sustains and the mountain's channel, and they persist through the night, lightning firing at a rate that has been estimated at roughly 28 strikes per minute at peak activity. Over the course of a year, the site produces somewhere in the range of 1-2 million lightning bolts. The phenomenon is called the Relámpago del Catumbum, the lightning of the Catumbum, and it has been occurring, as far as historical records suggest, for as long as the lake has been observed. The light from these storms is visible from extraordinary distances. Reports from sailors navigating the Caribbean in the 16th and 17th centuries describe a persistent glow on the southwestern horizon that could be used to establish position at night, in the same way a lighthouse serves navigators today. A fixed light at a known location that tells you, by its angle and bearing, where you are on the water. The Catumbu lightning was consistent enough, persistent enough, and visible from far enough away that it functioned as a natural beacon for open ocean navigation. A ship working its way along the Venezuelan coast in the 17th century, 200 miles out from shore, could see the storms above Lake Maracaibo flickering on the horizon and use them to fix a bearing. That persistence is worth sitting with for a moment. A lighthouse is reliable because someone built it and maintains it and keeps the light burning. The Catumbun storms are reliable because of a set of atmospheric and geographic conditions that assemble themselves night after night, season after season, powered by the sun heating the lake and the mountains shaping the wind. No one built it, no one maintains it. The conditions simply hold, and the storms form, and the lightning fires, and the light reaches out across the water to wherever a navigator happens to be waiting for a reference point. There were nights when the lightning was the only light visible anywhere on that stretch of coastline, the stars above, and the Katumbu storms to the southwest, and the dark water between. Sailors would have known the rhythm of the storms, known that they fired in the evening and persisted through the night, and quieted by dawn, known which season brought the most activity and which brought relative quiet. The storms would have been as much a part of the navigational landscape as any island or cape, a feature of the world to be read and used. The surface of Lake Maracaibo in those conditions, on a night well into storm season, holds a particular quality of light. Not constant illumination, the lightning does not sustain a steady glow, but a rhythmic, irregular brightness that comes and goes across the water, each flash illuminating the lake's surface for an instant before the dark returns. The far shore, miles distant, becomes briefly visible and then disappears again. The mountains to the south and west emerge for a moment from the darkness, with each flash, their silhouettes clear for that fraction of a second, and then gone. The water reflects the light downward, as well as receiving it from above, so that the lake itself seems to be part of the electrical system, lit from both directions at once. The storms produce rain. Of course, the condensation and updrafts that drive the electrical activity also produce precipitation, but the dominant quality of the night above the lake is not the rain. It is the light, the way it arrives and departs, the way it never quite settles into a pattern regular enough to predict, but never quite stops long enough to feel like it has ended. Ships passing 200 miles to the north would have seen this as a faint, irregular pulse on the horizon, nothing more. From the lake's edge, from the mouth of the river itself, it would have been something else entirely, a sky in constant electrical negotiation with itself, the lake below it, reflecting that negotiation back upward in the dark water. What makes the Catatumbo storms function as a navigational reference? What made them reliable enough that sailors crossing hundreds of miles of open Caribbean water could depend on them is the same thing that makes them unusual as a phenomenon. They are not a storm in the sense of a system passing through. They are a recurrence, a process that the local geography enables night after night. The warm water of the lake evaporates and rises. The mountain ranges channel the converging air masses and the trade wind moisture into the valley above the delta. The resulting updrafts are powerful and consistent enough to sustain convection through the night. The conditions are specific enough, and they hold closely enough to the same configuration from night to night, that the result has been continuous for as long as anyone has kept records, and almost certainly for much longer than that. The physics of it is not particularly different from the physics of any other thunderstorm. Warm, moist air rises, cools, condenses, charge separation occurs in the cloud as ice crystals and supercooled water droplets interact, and eventually the electrical potential becomes large enough that the air can no longer resist it. A leader forms, a channel completes, a return stroke fires. Thunder rolls across the water. This is what thunderstorms do. What makes the Catatumbo different is only that all the inputs that drive this process, the warm lake, the converging air masses, the mountain geometry, are arranged in a configuration stable enough to reproduce the result almost every night for most of the year. And 60 miles above those storms, in the quiet upper mesosphere, sprites are almost certainly forming. The right polarity, the right power in the return strokes, the right conditions in the upper atmosphere on any given night, there is no particular reason the Catatumbo storms would not produce them. They have been producing them in all likelihood for centuries, unobserved and unrecorded, because no one was looking at that part of the sky with the right instruments until very recently. The sailors using the storms as a navigational beacon saw the flash, the ground received the sound. The mesosphere, 60 miles up, was doing something else entirely. Quietly, in the dark, the idea that a storm can be doing several things at once at very different altitudes in very different physical regimes, with the lower events visible from the ground and the upper events completely invisible without specialized equipment. This is one of those features of the atmosphere that the scale of ordinary experience makes easy to miss. Storms look like they end at the cloud top. The visible boundary of the cloud is the visible boundary of the event. But the electrical system has no obligation to stop where the cloud does, and it does not. What was confirmed in 1989, when that Minnesota researcher's camera caught a sprite by accident, is that the atmosphere is electrically active in ways that had been present the entire time, happening above every major storm system across the planet, and simply waiting for someone to point an instrument in the right direction. The sprites had been there. The elves had been there. The upward leaders from tall structures had been occurring every time the conditions were right. The Catatumbo storms had been firing their lightning into the lake and the sky and the mesosphere above for centuries. None of it was new. The documentation was new. That is a particular kind of discovery, not the discovery of something that began to exist when it was found, but the recognition of something that had been continuous and uninterrupted and simply unrecorded. The atmosphere had been keeping its own account the whole time. The lightning channel that lasts 0.2 of a second and reaches 54,000 degrees is happening somewhere over the planet right now, as it was happening before anyone measured it. As the return stroke traveled upward along the completed channel before anyone had confirmed with high-speed photography that it did. The measurement does not change the thing. It only makes the thing visible in a way that fits the form of human knowledge. It is worth following that lightning channel one more time, not toward the upper atmosphere but sideways, into the air immediately surrounding it. In the moment of a return stroke, the air within the channel is briefly at 5 times the surface temperature of the sun. The air 1 centimeter outside the channel is at ordinary sky temperature. That boundary, that distance from scorching to ambient, is essentially the width of the channel itself, a few centimeters at most. The energy of the stroke is contained, for those 0.2 of a second, in an extremely narrow cylinder. The surrounding air does not gradually absorb the heat in the way a heater would warm a room. The expansion is too fast for that. The air at the channel boundary is simply displaced outward by the pressure, and that outward displacement is the shock wave, and the shock wave is what produces thunder. A tree near a lightning strike shudders not from the heat, which does not have time to propagate meaningfully, but from the pressure wave, the air displaced outward by the rapidly expanding channel. The sound that arrives a few seconds later is the same event at the speed of sound rather than the speed of light, delayed by the distance the wave traveled through air rather than through the conductive channel. By the time the thunder arrives, the channel itself has been gone for those same few seconds, the air having cooled back to ambient, the electrical gradient having equalized, the sky where the bolt was already unremarkable again. The impression that a bolt of lightning is a long event, a sustained illumination, a presence in the sky, comes from the persistence of the visual signal in the eye's processing, and from the fact that most lightning flashes involve multiple strokes along the same channel in rapid succession, each re-illuminating a channel that has only partially cooled. What looks like a single sustained flash is often 3 or 4 distinct strokes, each lasting about 0.2 of a second, separated by milliseconds. The channel flickers. The eye averages the flicker into something that appears continuous, 2/10 of a second, 5 times the surface temperature of the sun, a channel a few centimeters wide, and then 60 miles above, a reddish jellyfish shape blooming for a few milliseconds in the mesosphere, invisible from the ground, detected for the first time by a camera pointed in the wrong direction for a different purpose entirely. And above that, an elf expanding outward at 300 miles in diameter in 1 millisecond, lit by the electromagnetic pulse of the same stroke, too fast for any human sense to register. And on the water south of the Caribbean, on a night in October when the season is fully open, the Catatumbo storms are doing this continuously, striking 28 times a minute above the mouth of the river, the lake below reflecting each flash in its dark surface, the far shore appearing and disappearing in the irregular rhythm of the light. 200 miles to the north, on a ship working its way along the coast with the stars above and the horizon dark in most directions, a navigator has turned to the southwest because that faint, repeated brightening is the one fixed thing in the dark, not a star, not a fire on land, but the sky above Lake Maracaibo doing what it does every night, the lightning as reliable as anything built and maintained by human intention, the light traveling across open water to wherever someone happened to be waiting to use it. The storms will still be there in the morning when they fade, and in the evening when they return. The channel above the delta that will carry the next return stroke is not yet formed. It will form when the conditions are right, the lake warm, the mountains channeling the air, the charge separation in the cloud reaching the threshold the air can no longer hold. Then a leader will step downward, and a streamer will rise, and the channel will complete, and for 2/10 of a second, a column of air above the water will be briefly hotter than the surface of the sun, and the light will reach out across the water, and somewhere a navigator who knows the waters well enough to read it will take a bearing, and the thunder will follow, rolling across the lake in the darkness, and the water will hold the last of the light for just a moment before the dark comes back. In a yard in Vivian, South Dakota, on the afternoon of July 23, 2010, there was a piece of ice lying in the grass that was roughly the size of a person's head, not a softball. Larger than that, larger than a fist by a considerable distance, larger than most people's hands laid flat. Someone who had gone to her door to look at the storm had stepped outside afterward and found it there, and the first problem was working out how to carry it, and the second problem was working out where to put it. And by the time she had solved both of those problems, she had also understood that she should not let it melt. That hailstone would be measured at 8 inches in diameter. It would be weighed at 1 pound and 15 ounces. It would be certified as the largest hailstone ever officially recorded in the United States, a record it still holds. But before any of that happened, it was simply a very large piece of ice in a yard in South Dakota, sitting in the summer grass, and the person who found it needed something to carry it in. When researchers eventually cut that hailstone open, what they found inside was a cross-section that looked in its way like the interior of a tree. There were rings, concentric layers of ice, one inside another, each one representing a single pass upward through the body of the storm. A hailstone grows the way it does because it begins as a small frozen nucleus and is then carried upward by the storm's updraft into colder air, where new moisture freezes onto its surface. Then gravity pulls it down again. Then the updraft catches it once more and carries it back up. Each loop deposits another layer. The Vivian stone, by the count of its rings, had made that circuit many times before the updraft finally gave out and let it fall. What came down through the roof of the storm that afternoon had been built slowly, layer by layer, in the dark interior of a cloud, over the course of its repeated journeys between cold and colder. The storm that produced it was not a quiet one. The updrafts capable of suspending a nearly 2-pound piece of ice in the air, long enough to build it to that size, are moving at speeds that can hold a human body aloft. The energy required is genuinely considerable. A storm producing hailstones of that size is a storm in which the air itself is working with unusual force, and still the object left behind in the grass was not a piece of destruction to look at. It was a piece of ice, rounded, heavy, strangely smooth in places. Its interior, when it was finally cut, was clear enough that you could see the layering, and the layering was precise enough to be counted. Ice has a way of recording what happened to it. The rings in a hailstone are a kind of compressed diary of the storm that made it, how many times the stone went up, how cold each level was, how much moisture was available at each altitude. A frozen record of circuits completed in the dark inside a cloud, none of which anyone witnessed. What the stone carries out with it, when it finally falls, is everything the storm put into it on the way. There is a town called Lajamanu in the Northern Territory of Australia, remote enough that most maps of the country do not include it. Sitting on the edge of the Tanami Desert, more than 500 miles from Darwin, it has a small population, a school, a health clinic, a community store. What it also has in its recorded history is a documented instance of fish falling from the sky. Not a single fish, not a small number of fish, hundreds of small perch raining down on the town in April of 2010. And then, 2 days later, it happened again. The same fish, the same sky, the same open, arid ground of the Northern Territory, with no body of water anywhere near. The fish were small spangled perch, a species native to inland Australian waterways. They came down alive. Residents found them on the ground still moving, still attempting the motions of swimming, on dry red earth under an open sky, from which no significant rain had fallen. The children at the school reportedly collected them. The adults tried to work out what had happened. The explanation that has continued to hold up, the one that has been applied to similar events documented at various points throughout recorded history in different countries, involves a water spout or a tornado passing over a body of water somewhere well to the south, lifting fish and water together, carrying them within the storm system, and then releasing them when the updraft weakened over the settlement. What that explanation requires is that the fish survived the journey, and apparently they did. Small fish can survive a period of time suspended in water inside a storm cell if the temperature is not extreme and if they are deposited quickly enough. The updraft that lifted them would have been powerful enough to suspend them in cool, moist air, and the air inside a storm column is not dry in the way the desert floor beneath it is dry. The conditions, strange as they are to picture, can be survivable. The fish arrive alive because the storm, in some sense, preserved them in transit. 2 days between the events is the detail that invites the most attention. It suggests that whatever system produced the first rainfall of fish was large enough, or slow enough, or the fish distributed enough within it, that a second deposit was possible. Possibly the storm carried 2 distinct accumulations. Possibly a trailing cell dropped what the first had not. The precise sequence is not something anyone observed from inside the cloud. What was observed was the result, twice over, on the same ground, in the same remote settlement, under the same wide Northern Territory sky. It is worth holding for a moment what it actually looks like to find a fish on the ground in a desert town where no water is nearby. The fish is small and silver and unmistakably alive. The ground around it is red dust. The sky is clear or nearly clear by the time the finding happens, because the storm has passed. There is no water visible anywhere in any direction, and the fish is there regardless, moving. The ordinary rules of where fish can be seem to have simply not applied for long enough to place one here. The Atacama Desert in northern Chile runs for roughly 600 miles along the Pacific coast, pressed between the Andes Mountains to the east and the cold Humboldt Current to the west. In some parts of its interior, meteorological records show no measurable rainfall for stretches lasting 40 or more consecutive years. Not low rainfall, not infrequent rainfall, no rainfall that any instrument placed there managed to detect for decades at a time. The soil in those areas is so dry and so undisturbed that researchers studying it have found organic compounds preserved within it that would have decomposed in the presence of any moisture at all. And yet, things live there. Not many things. Not the usual density of life that even other deserts support. But there are plants. There are communities of specialized organisms clinging to the surfaces of translucent quartz pebbles, beneath which they can photosynthesize in protected conditions. There are cacti with root systems engineered for efficiency, and there are plants along the coastal margins of the desert that have solved the problem of the missing rain in a way that makes no reference to rain at all. Each morning, from the cold surface of the Humboldt Current offshore, a fog bank forms and begins to move inland. It is dense and low and white, and it has a name, Camanchaca, from the Aymara word for the fog itself, a word that describes something close to the feel of it, which is the feel of cloud at ground level, thick enough to be wet, cold enough to leave a film on a window. The fog rolls across the coastal slopes of the Atacama, and the plants that live in its path collect moisture from it directly on their surfaces, not from rain pooled on the ground, not from underground water reaching them through roots. From the air itself, from contact with the fog, the moisture depositing on leaves and stems and running down to the soil around the base of the plant in quantities small enough not to be measurable as rainfall, but large enough apparently to sustain life. Some communities in the driest parts of the Atacama's margins have installed what are called fog collectors, large mesh nets stretched vertically on frames, positioned to intercept the Camanchaca as it moves inland, and the water that drips from these nets into collection basins below, in some locations the only fresh water available. The fog does not announce itself the way rain does. It does not arrive with a change in pressure or a shift in temperature that anyone on the ground would recognize as weather approaching. It simply comes every morning from the sea, and then it retreats, and the plants that learn to drink from it are still there in the afternoon sun, on bone-dry ground with no rain in the soil for as far as a root could possibly reach. The Atacama's interior zones, the places with those 40-year gaps in the rainfall record, are quiet in a way that most landscapes are not. The soil is pale and fine, the horizon is flat in most directions. There are salt flats that look from above like snow, but are dry and crystalline, and yield nothing when tested for moisture. The sky above them is almost always clear, a hard blue with very little haze, because haze requires moisture, and moisture does not come here. The absence of rain in this place is not a temporary drought or a seasonal pattern, it is the baseline condition. Life in the Atacama is not waiting for the rain to return. It has organized itself around the premise that rain is not what is available. Deep inside the planet Neptune, at pressures that are difficult to describe in terms of anything a person might encounter in ordinary experience, scientists have hypothesized that something unusual may be happening to carbon. Carbon under ordinary conditions behaves in the ways that carbon usually behaves. It forms organic compounds. It bonds with other elements. It turns up in coal and graphite and the material of living things. Carbon under extreme pressure does something else. It becomes diamond. The interior of Neptune is estimated to reach pressures millions of times greater than atmospheric pressure at Earth's surface and temperatures of thousands of degrees. Under those conditions, models of planetary chemistry have suggested for some years that the carbon-rich compounds in Neptune's interior might be compressed directly into diamond structures, which would then sink through liquid carbon toward whatever solid core the planet might have beneath its fluid layers. The image this produces, diamonds forming in the atmosphere of another planet and then falling through liquid carbon toward the planet's center, has a quality that is difficult to categorize. It is not rain in any sense that connects to standing outside in a storm, but it is precipitation in the technical sense, material forming in one part of a fluid environment and falling through it toward a denser region below. In 2017, researchers at the SLAC National Accelerator Laboratory in California produced experimental evidence that this process is physically plausible. They took a hydrocarbon compound, a simple one, not unlike materials found in the outer atmospheres of ice giant planets, and subjected it to conditions approaching those estimated for the deep interior of Neptune and Uranus, using a high-powered laser to generate the required pressure in an extremely small sample for an extremely brief period. What the instruments recorded in that instant was the formation of diamond structures within the sample, not hypothetical diamond structures, not modeled ones, actual nanoscale diamond formations produced under laboratory-generated pressures by a process that, if the models are correct, is occurring right now inside a planet more than 2 billion miles from where the experiment was conducted. The laboratory involved is at a location in Menlo Park, California, which is unremarkable in appearance, a research facility with buildings and parking lots, and the ordinary surfaces of a working institution. The interior of the accelerator hall, where the laser platform is housed, is more unusual, a long room designed around instrumentation of considerable precision. The sample in the experiment would have been almost invisibly small. The laser pulse that hit it lasted for a fraction of a second, and in that fraction of a second, under those conditions, something that falls from the inside of Neptune formed inside a room in California. Briefly, before the pressure released and the measurement was taken and the sample returned to what it had been. Diamond rain is the phrase researchers have used in describing this. It is a phrase that sits oddly because diamonds are not soft or fluid, and rain is. What the phrase is pointing at is the idea of a continuous gravitationally driven fall of something through a planetary interior, a slow precipitation of dense crystalline carbon through liquid carbon toward a solid center on a time scale and at a depth that no instrument will ever directly observe. It is a feature of another planet's interior weather, in the broadest sense of that word, and the evidence that it might be real came from a room-sized instrument applying a laser pulse to a sample smaller than a grain of sand. At various points over the past several decades, in Spain and the United States, and Brazil and India, large pieces of ice have landed on the ground under clear skies with no storm present anywhere in the vicinity. Not small pieces. Not the sort of ice that might form on the hull of an aircraft and fall off during descent. Large masses, some of them weighing several pounds, found in open fields and on roads and in the gardens of private houses by people who heard something land and came outside to find it there. These objects have a name now, megacriometeors. It is a name that was developed as researchers began to take the phenomenon seriously enough to study it, and it applies to any anomalously large mass of ice falling from a clear sky outside of any conventional weather event. The first challenge the name was meant to address was the obvious initial assumption, which was that these pieces of ice had to have come from aircraft. Aircraft do sometimes shed ice. Wastewater tanks on older aircraft have occasionally failed, producing large frozen deposits that fall to the ground when altitude and temperature allow. But the pieces recovered in the documented megacriometeor cases have been subjected to isotopic analysis, a process that examines the specific chemical signatures of the water molecules within the ice. And what that analysis has consistently found is that the ice carries signatures matching atmospheric water, not aircraft wastewater, not ice from an industrial source. Water that was, at some point, suspended in the atmosphere in the form of vapor before becoming this, the mechanism by which atmospheric water vapor could accumulate into a mass of several pounds of ice and then fall from a clear sky, is the part that remains open. There are hypotheses. Some involve the role of the upper atmosphere in particular jet stream conditions. Some involve interactions between aircraft and upper-level air in ways that are different from the waste tank scenario. None of them has been tested and confirmed to the satisfaction of the researchers who have looked most carefully at the question, partly because the events are infrequent and unpredictable enough that no one has positioned instruments to observe one in progress. What is known is the chemical signature of the ice and the fact that the sky above it was clear when it landed, and those two facts together constitute a genuine open question rather than a solved one. The ice, once found, melts. This is obvious but worth noting because it places a limit on how long any specimen remains available for study. The researchers who have worked on this question have in several cases received calls from members of the public who have found a large piece of ice in an open field and have done the sensible thing, which is to put it in their freezer before calling anyone, which is exactly what needs to be done if the sample is going to be preserved. The Vivian hailstone also ended up in a freezer. Ice that carries information has to be kept cold for that information to remain available, and keeping it cold requires someone to recognize quickly that it is worth keeping. There is something particular about the way the Atacama plants collect their water that rewards a second look. The structures on the surfaces of some of these plants, small hairs, fine textures, waxy coatings angled in specific directions, are not general-purpose features. They are shaped by a long process of selection toward the specific problem of collecting moisture from air that moves across them in a particular direction at a particular time of day. The Comanchica moves inland in the morning from west to east, and the plants in its path that have survived are the ones whose surfaces were best suited to catching it. The others, over time, were not there to reproduce. What remains is a community of organisms whose entire physical architecture is organized around a fog bank that arrives each morning from the sea. The fog collectors that human communities have built in the Atacama are a kind of acknowledgement of the same principle, that the moisture is there, in the air, even when no rain falls, and that the problem is not the absence of water, but the absence of a surface for it to collect on. The mesh of a fog collector works the same way as the fine hairs of a coastal desert plant. The water is in the fog. Something has to stop it and let it pool. On a clear morning in the Atacama, standing at the edge where the coastal zone gives way to the interior, the experience is of watching two different versions of the world occupy the same landscape. Behind, toward the sea, the fog is still present, low, thick, moving slowly. Ahead, In the interior, the air is bright and absolutely dry, and the ground holds no moisture at all that any instrument would record. The line between them shifts slightly with the wind and the time of day. The plants that live in the fog zone are in a different world from the rock and salt and dust of the interior, separated not by any visible barrier, but by the difference between air that is marginally wet and air that is not. A large piece of ice in a Spanish garden on a clear afternoon in summer is an object that sits outside the ordinary explanations that people apply to things they find outside. Ice in summer means something released it from somewhere. A clear sky means no storm. No storm means the usual mechanism is not available. The person who found the one in Spain, or the one in India, or the ones in the United States or Brazil, had the experience of standing in front of something that did not fit the categories they had available for it. Not because it was impossible. Isotopic analysis confirmed it was atmospheric water, not something manufactured, but because the category it belongs to is one that most people have never needed. The fish in Lajamanu fit a known category once explained. Waterspouts carry things. Fish are light enough to be carried. The storm deposits them when the updraft weakens. Every part of the mechanism is physically real and individually unexceptional. What the explanation requires is simply that several things happened in the right sequence, at the right place, and that someone was in the town of Lajamanu to find the result. Most of the fish that waterspouts have ever lifted have probably fallen into water, or into empty land, or into the sea without anyone being there to record it. The Lajamanu events are documented because there were people there, and the people recognized what they were looking at as unusual, and the fish were still moving. The diamond structures that formed inside the SLAC laser chamber in 2017 did not persist after the pressure was released. The experiment was not designed to produce lasting diamonds. It was designed to produce conditions and to measure what happened under them, and the measurement confirmed that the conditions produced diamond formation. The diamonds themselves were gone in the same fraction of a second that the pressure was. What remained was the data, and the data said that under pressures matching those deep inside Neptune, a hydrocarbon compound will organize itself into a crystalline carbon structure. The implication that this is happening right now inside a planet billions of miles away, on a scale and at a depth that no probe has ever reached, follows from the data but does not require the diamonds in the laboratory to have been kept. It is the nature of ice to carry information briefly and then release it. The rings in the Vivian hailstone, legible on the day it was cut open, would become illegible as the stone melted. The megacriometeors left their chemical information in the isotopic ratios of their water molecules, and those ratios could be measured while the ice was intact, and the measurement said this came from the atmosphere. After that, the ice melted too, and what was left was the measurement and the open question of how. The Atacama's Camanchaca comes every morning, regardless of whether anyone is measuring it or collecting it. The plants that collect it do not record the collection. The fog rolls in from the sea, deposits its moisture on whatever surfaces interrupt it, and retreats before mid-morning when the sun warms the coastal slopes enough to dissolve it. This has been happening for as long as the cold Humboldt current has been running along that coast, which is a very long time, and the desert's interior has been dry for that entire period, and the life at the coastal margin has been drinking from fog for all of it. The hailstone that landed in Vivian came from a single storm on a single afternoon in July. It took the storm a considerable and unknown number of updraft cycles to build it to the size it reached. When the updraft finally failed to hold it, it fell, and it was found, and it was carried inside, and it was kept cold, and it was measured, and it was cut open, and the rings inside were counted, and it is still officially the largest hailstone ever recorded in the United States by the standards of the measurements that apply to such things. Somewhere above Vivian, that afternoon, the storm that made it is no longer present. The sky over South Dakota has been ordinary since then, in the way that skies over ordinary places are ordinary. What the storm left behind was an object in a freezer, and the record attached to it, and the image of those concentric rings, each one a circuit completed in the dark. A megacriometeor lands on the ground and immediately begins returning to the state that water normally occupies in a landscape where the air temperature is above freezing. The window in which it can be examined is short, and the window in which it can be properly analyzed with the equipment needed for isotopic measurement is shorter still. The researchers who have built the most complete understanding of these objects have done so by being reachable when someone calls, and by moving quickly when a call comes in, and by being the kind of people who keep the relevant equipment on hand for an event that cannot be predicted and might not happen for years. The resulting body of knowledge is partial, as all bodies of knowledge about infrequent and unpredictable events tend to be. What it contains is enough to confirm that the ice is real, that the sky was clear, that the chemical signature matches atmospheric water, and that the rest of the question remains exactly where it was. The plants of the Atacama's coastal margin do not make any reference to rain in their architecture. Their root systems are not particularly deep. Their water-collecting surfaces are oriented toward the morning fog. They are, in a structural sense, a record of what has been available in this place for long enough to shape a living thing. The fog comes from the cold ocean. The plants collect it. The interior of the desert remains dry. These are separate conditions that coexist without resolution, and the border between them shifts slightly each morning and each afternoon, and nothing in that process is waiting to be resolved. The spangled perch and Lajamanu were by most accounts doing reasonably well when they were found. Small fish are adaptable in ways that seem from the outside almost unreasonable. The ones that survived the journey through the storm and the deposition on red desert earth were, at the moment of their finding, still attempting to swim. The ground they were on offered them nothing useful. The sky above them was clearing. The storm that had carried them was moving away or had already dissipated, and still they were there, moving on dry ground in the Northern Territory, 2 days in a row, under a sky that had not produced any rain worth measuring. The ice in the freezer in Vivian was carefully tended and transported when needed, and eventually became the official record it now officially is. The rings inside it are documented. The diameter is documented. The weight is documented. What is not documented, because no one was there to see it, is the interior of the cloud above Vivian on the afternoon of July 23rd, 2010, the updraft velocities, the temperature at each altitude, the number of cycles the stone actually completed, the precise moment the updraft lost the ability to hold it. Those things happened and produced the stone, and the stone carries their compressed record in its rings, but the direct observation of them is not something anyone has. The stone is the evidence of a process that was completed privately, in the dark interior of a cloud before the stone fell into the light, and somewhere far below the surface of Neptune, under pressures that no instrument built on Earth has ever directly experienced, carbon compounds are doing what carbon compounds do under those pressures, according to the models built from laboratory measurements conducted on samples smaller than a grain of sand. Whether the diamonds that form there sink, and at what rate, and what accumulates at the planet's core over the timescales involved, these are questions that the measurements point toward and do not fully answer. The planet continues regardless. The pressure inside it is not waiting for a confirmation. The process, if it is the process the models describe, has been running since the planet formed, and the diamonds, if they form, fall in a darkness and at a depth where the word fall is stripped of almost everything it usually carries, and what remains is only the physics of a denser thing moving through a less dense thing, under conditions that no one has been there to see. A large piece of ice lying on open ground in Spain on a summer afternoon under a cloudless sky is an object that carries a question with it. The analysis of that question has produced a partial answer. The ice came from atmospheric water, and an honest acknowledgement that the rest of the question is one that researchers are still working through. The ice, by the time the acknowledgement was written down, had melted. The sky above the spot where it landed was still clear and unremarkable and offered nothing by way of explanation. And that, quietly, is where the question sits, not closed, not urgent, not demanding anything of the person who finds themselves thinking about it, just open and out there in the way that the best questions tend to remain. On a ridge in the Harz Mountains of northern Germany, in the early hours of a morning when the valley below has filled entirely with fog, a hiker stands with the sun rising behind them. The light comes over their shoulder. It reaches past them and down into the white surface below, and there, in the mist, something appears. A shadow. Their shadow. But not the small compressed shape a person casts on a footpath. This one stands enormous in the fog, 2 or 3 times a human height, its edges soft and slightly trembling where the mist shifts. Around it, if the conditions hold exactly right, a set of concentric rings forms, faint greens, pinks, and blues, arranged in halos, perfectly centered on the shadow's head, as though the figure in the mist is wearing something around its own outline. For a moment before understanding arrives, the hiker is simply standing there, looking at it. The phenomenon has a name, taken from the Brocken, the highest peak in the Harz Range, where it was historically observed and documented. The Brocken specter. It appears when a person stands with sunlight behind them and a bank of fog or cloud below, and what they see in the mist is their own shadow, projected and enlarged by the geometry of the angle between the light and the surface it falls upon. The colorful rings surrounding the shadow are called a glory, and they form through a different mechanism than a rainbow. In a rainbow, the light bends through each droplet and refracts into its spectral components on the way out. In a glory, the light enters a water droplet and then, through a combination of refraction and diffraction, curves around and back toward its own source, so the colors are seen by the person standing in precisely the direction from which the light came. This means the glory is always perfectly centered on the shadow's head. It follows the observer's own line of sight exactly, which is why no 2 people standing on the same ridge see their halos in the same place. Each one sees the circle centered on themselves, on their own shadow, wherever it falls in the fog below. The droplets have to be nearly all the same size. That is the condition that makes the colors appear sharp and ordered rather than washed into white. Young clouds, freshly formed from water of uniform temperature and composition, tend toward this uniformity, which is why a glory seen on a fresh fog bank is often more vivid than one seen on older, more varied cloud. The Harz Mountains see this more reliably than most places, because their ridge lines catch the morning sun while valley fogs are still settled and young before the afternoon warmth begins to mix the air and break the droplets into varied sizes. Pilots of small aircraft see glories more often than hikers do, the shadow of the aircraft projected onto cloud below, ringed in the same soft colors, the center always exactly where the pilot's own eye is aimed. The atmosphere does things with light that take a moment to credit, even when the mechanism is clear. What the Brocken specter illustrates more than any specific optical formula is that the sky is not uniform. It has layers and textures and physical structures built from water and temperature and the angle of incoming light, and those structures interact with that light in ways that produce forms no one would necessarily predict from first principles alone. The atmosphere is not a backdrop, it is a medium, and things happen inside it. Some of those things happen far above any ridge a hiker stands on. Nacreous clouds form between 15 and 25 kilometers above the Earth's surface. In the lower stratosphere, far above the weather systems that produce ordinary clouds. At that altitude, air is extremely cold and extremely dry, and nacreous clouds form only in polar winters, when temperatures in the stratosphere drop low enough, below roughly minus 85 degrees Celsius, for what little water vapor is present to crystallize into ice particles of very nearly identical size. The word nacreous comes from nacre, the lustrous material inside a shell. The clouds take their name from what they look like. They are seen after sunset. That is the condition. The lower atmosphere must already be in shadow, the sun below the horizon, the sky at ground level dark enough that ordinary clouds have gone gray and formless. But at 20 kilometers altitude, the stratospheric clouds are still fully lit. The sunlight still reaches them from below the horizon because they sit so far above the curve of the Earth, and in that late-angled light, the ice crystals diffract the incoming wavelengths into colors that have no equivalent in ordinary weather. Electric pink, vivid green, a blue that shifts toward violet at its outer edge. The colors move as the angle of the light changes, the entire cloud rippling through its spectrum as the sun continues descending below the horizon and the angle narrows. In Antarctica and the high Arctic, where the winter sun barely clears the horizon before returning below it, nacreous clouds can be seen for extended stretches of twilight. Researchers at polar stations have described the experience of watching them from outside. Standing in minus 40 degrees on the surface, the sky at eye level fully dark, and 20 kilometers above, these luminous, iridescent forms drifting slowly in winds that move at speeds the surface instruments cannot even register from this distance. The clouds are not dramatic in the way of thunderstorms or lightning. They are quiet. They hang there and glow, and the colors are so saturated and so structured that photographs of them consistently look adjusted, even when they are not. Cloud iridescence is a simpler, more accessible version of the same optical effect, where nacreous clouds require stratospheric conditions and polar winters. Iridescence can appear on any young cloud with droplets of sufficiently uniform size anywhere in the world. It tends to show up at the edges of fresh cumulus clouds, where the droplets are most recently condensed and most similar in size, as faint patches of green and pink along the cloud's margin. Most people pass under clouds their whole lives and never notice these colors, partly because they are looking at the main body of the cloud rather than its edge, and partly because the colors are not always present. They depend on that uniformity of droplet size, which the cloud works against over time as it grows and its droplets merge and vary. The brightness of iridescence on an ordinary afternoon cloud is modest. On nacreous clouds at 20 kilometers, lit from below by a sun that has already set from the perspective of the ground, the same effect reaches an intensity that has no comparison in anything that happens in the lower atmosphere. The physics are the same. The conditions are simply more extreme, more precisely right, and located in a layer of the atmosphere that most people spend their whole lives not thinking about. The sky has more layers than the clouds most people look at. That is a plain fact, and the atmosphere keeps filling it in from the stratosphere downward through ice crystal displays and colored halos and the particular optical behaviors of water droplets at different temperatures. Below the stratosphere, in the layer of air where weather happens, the structures that form are determined by heat, moisture, and the movement of air masses, and those structures range from the familiar to the genuinely unexpected. The morning glory is a cloud most people have never seen, and most of the world will never see, because it appears reliably in only one region, over the Gulf of Carpentaria in northern Queensland, Australia. Between September and November, a tubular cloud sometimes forms and rolls across the sky at low altitude, anywhere from 100 meters to 2 kilometers above the ground. It can stretch for hundreds of miles from end to end. Along its length, the cloud rotates slowly around its own horizontal axis, the leading edge curling downward and the top edge curling back, so the whole structure moves like a slow roller across the water and the flat land at its edge. The town of Burketown in remote northwestern Queensland is the place where glider pilots travel specifically to encounter it. The morning glory rolls in during the morning hours, typically around dawn, and as it passes, the pressure changes in front of it, produce a band of rising air along the leading edge that glider pilots can use to climb without an engine. This is called an atmospheric bore, and the morning glory is the visible manifestation of one. Two converging sea breeze systems, one from the Gulf of Carpentaria and one from the Coral Sea, coming from roughly opposite directions across the Cape York Peninsula, generate waves of pressure along the boundary between the incoming air and the air in place. Those waves propagate along the surface of a temperature inversion, and where the wave lifts the air above it, the moisture condenses into the rolling cloud. The cloud does not stay in one place. It travels with the pressure wave, rolling forward slowly, its rotation visible if the observer is close enough and the light is good. To see it from a glider is to have the leading edge of something enormous passing a short distance above and ahead of the aircraft, the cloud rotating, the lift from the pressure change carrying the glider upward without any power at all. Pilots who have made this flight describe the experience of flying parallel to a cloud wall that goes from near the ground to above their altitude, moving at roughly 60 kilometers per hour, lit from behind by a low morning sun. The cloud is long enough that from one end, the other is not visible. It is simply a horizon in itself, a moving wall of gray and white that goes north and south as far as the eye can reach. The formation requires the convergence of the two sea breezes, which is why it appears seasonally. The atmospheric conditions that bring those breezes into contact only occur reliably in the October and November period, and why it appears over this particular geography. The Gulf of Carpentaria is a shallow, enclosed sea that generates a strong local sea breeze with particular consistency. The peninsula to the east lets the Coral Sea breeze reach far enough inland to meet it. Somewhere in between, on mornings when the conditions are exactly right, the morning glory rolls in from the northeast and crosses the coast before dispersing in the heating of the day. Outside of this region, atmospheric bore waves exist, but the visible, low-altitude rolling tube cloud they produce here is essentially unique to Carpentaria. Researchers travel to Burketown to study it. Pilots travel there to fly beside it. Most people in the world will not spend enough time in remote northwestern Queensland in late October to have any particular reason to know it exists at all. There are clouds that form from fires. This sounds like a category error. Fire produces smoke and heat, not moisture, But the distinction between what a large fire produces and what a storm requires turns out to be narrower than it might seem. When a wildfire grows large enough and burns with enough intensity, the column of superheated air rising from it can reach the lower troposphere. That column carries not just heat and smoke, but moisture, water released by the burning vegetation, water evaporating from soil, water in the combustion process itself. If the column is powerful enough and rises high enough into air that is unstable, the moisture it carries can begin to condense. Cumulonimbus clouds form when rising moist air encounters the right atmospheric conditions at altitude. A pyrocumulonimbus cloud forms through the same mechanism, except the rising column is not driven by the sun warming the surface, but by a fire below. The distinction matters because a pyrocumulonimbus is a full thunderstorm, not just a tall cloud, a storm system with the same internal dynamics, updrafts, downdrafts, ice formation at high altitude, charge separation between regions of positive and negative particles, and ultimately lightning, as any other thunderstorm. The cloud tops of pyrocumulonimbus formations have been measured at heights comparable to severe thunderstorms. They generate lightning. They produce downburst winds that emerge from their base as the internal downdraft hits the surface. They have enough internal circulation that once they reach a certain size, they begin to generate weather on their own terms, separate from the fire below. The bootleg fire in southern Oregon in the summer of 2021 produced pyrocumulonimbus clouds on multiple occasions. Fire behavior analysts monitoring the fire noted that on the evenings when pyrocumulonimbus formed, the fire's behavior became difficult to model. The storm system above the fire was generating its own winds that came down from the cloud's downdraft and moved in directions that did not match the regional weather patterns the models were using. The cloud was, in a precise sense, doing its own thing. It had crossed some threshold of size and internal energy where it was no longer simply a product of the fire, but a self-contained atmospheric system that happened to be anchored above the fire's strongest burning area. A pyrocumulonimbus cloud seen from a distance of 20 miles looks like a thunderstorm that someone has set on top of a column of dark smoke. The anvil top is the same shape as any other severe thunderstorm anvil. The cloud is lit internally by its own lightning. The smoke feeding into its base gives the lower part a different color than an ordinary storm, darker, browner, but from anvil to base, the structure is recognizably a storm system, and it is moving and generating weather with the same indifference to observation as any storm over open country. The fire analyst described the bootleg fire's pyrocumulonimbus as producing weather that existed beyond predictable modeling, which is a precise way of saying that the cloud had become something they were watching rather than anticipating. Thunderstorms over land make lightning. They also, through a less visible process, change the charge distribution across a much larger volume of atmosphere above them. High above a thunderstorm, at altitudes between 40 and 80 miles, the electrical activity below generates responses in the upper atmosphere that were not formally observed or documented until fairly recently, not because they were rare, but because they are brief, faint, and occur at altitudes where no ordinary camera or observer is pointed. Sprites are large-scale electrical discharges that appear above active thunderstorms at altitudes between roughly 40 and 80 miles. They are reddish in color, shaped something like a jellyfish, a central bright region with tendril-like extensions reaching downward, and they last only a few milliseconds before disappearing entirely. They are, by every measure, as real as ordinary lightning. They are produced by real charge differences. They produce real light. They are measurable by instruments, but they were not formally captured until 1989, when a researcher at the University of Minnesota aimed a low-light camera at the sky above a distant storm during an unrelated test. The recording of those first sprites was accidental. The researcher was not looking for them. They appeared in the footage while he was doing something else. The reason sprites went unnoticed for so long is simple. From below, looking up at a thunderstorm, the bright lightning and the illuminated clouds fill the visual field with light at the altitudes where the storm lives, below about 15 miles. Sprites form much higher than that. They are upward phenomena. The storm's downward lightning is vastly brighter than the sprites above, and the sprites last for a duration measured in milliseconds, which is shorter than the human visual system's ability to cleanly register a discrete flash. Pilots and astronomers had reported seeing odd flashes above storm tops for many decades before the 1989 footage, but without a recording, the reports were difficult to assess. Since the first accidental footage, sprites have been documented extensively. High-altitude research aircraft, space station cameras, and purpose-built instruments have captured them in enough detail to establish their structure, their altitude range, and their relationship to the lightning strikes below. A positive lightning strike, a less common type of strike that transfers positive charge from the cloud to the ground, appears to be particularly effective at generating sprites. The electrical disruption from such a strike propagates upward through the atmosphere and reaches the mesosphere, where the sprite forms. The light they emit is real and measurable, and it is reddish because the nitrogen molecules in the upper atmosphere, when excited by the electrical discharge, emit light in the red portion of the visible spectrum. The jellyfish shape is not a coincidence. The central region forms first, where the excitation is strongest, and then the tendrils extend downward along electric field lines, so the shape reflects the physical structure of how the discharge propagates through the thin air at that altitude. Above the altitude range where sprites form, another category of upper atmospheric electrical event takes place, and this one is not shaped like a jellyfish. It is shaped like a ring. When a powerful lightning strike sends an electromagnetic pulse upward, not the visible light of the strike, but the electromagnetic energy traveling outward from the channel, that pulse eventually reaches the ionosphere at around 60 miles altitude. The ionosphere is a region of the atmosphere where incoming solar radiation has ionized gas molecules, producing a layer of charged particles that is electrically active and responsive to electromagnetic disturbances. When the pulse from a powerful lightning strike arrives at this layer, it excites the ionosphere along a circular front that expands outward from the point directly above the strike. The result is a ring of light, expanding at the speed of light across the ionosphere, fading as it goes. The diameter of this ring can reach 300 miles from edge to edge. It lasts for only about a millisecond before it disperses, and it is silent, invisible from the ground, and recorded only by sensitive instruments in aircraft or on the International Space Station. The name for this phenomenon is an ELVE, sometimes written as LV, an acronym for emissions of light and very low frequency perturbations due to electromagnetic pulse sources, which is a technically precise label for something that behaves in the moment it exists, like a vast slow ripple spreading outward across the ceiling of the sky. Sprites and elves exist in the same general space, tens of miles above the storm below, and they involve the same storms that produce ordinary lightning. They are not unusual atmospheric events in the sense of requiring exotic conditions. They require only a sufficiently powerful thunderstorm, which is not a rare thing. What is rare, historically, is having an instrument pointing in the right direction at the right moment. The sky at 60 miles altitude is not somewhere that everyday observation reaches, and for most of recorded history, what happened at that altitude during a storm simply happened without any record of it. The atmosphere extends upward from the surface for several hundred kilometers before it thins into space, and almost all the weather that shapes daily life happens in the lowest 10 to 15 kilometers of that column. But what the upper atmospheric electrical events make clear is that a thunderstorm is not a phenomenon contained within itself. Its effects propagate upward into regions of the atmosphere that sit far above any cloud, reaching the ionosphere in the form of electromagnetic pulses, exciting the mesosphere in the form of sprites, and doing all of this in milliseconds while the storm below continues, unaware, generating the next lightning strike that will send the next pulse upward. What the London fog of December 1952 illustrates is a different kind of atmospheric structure, not optical, not electrical, but chemical and thermal, and produced not by the atmosphere's own processes, but by what was being put into it. In the first days of December 1952, London was cold. A high-pressure system had settled over the city and its surroundings, suppressing wind and reducing cloud cover, which allowed overnight temperatures to drop and allowed the air near the surface to cool into a dense layer that stayed close to the ground. Above this cold surface air, the temperature inversion, a layer of warmer air acting as a cap, held the surface air in place. Nothing was moving it upward. Nothing was flushing it sideways. It sat. Tonight in 1952 burned coal. Millions of domestic fireplaces burned it, along with industrial furnaces, power stations, and the gas works. The combustion products, sulfur dioxide, smoke particles, various other chemical compounds, entered the surface air layer and stayed there. The inversion held them. As the days passed, the concentration increased. The sulfur dioxide reacted with water droplets in the fog to produce sulfuric acid, and the mixture of fog, smoke, and acidic compounds that settled over the city between December 5th and December 9th was different from ordinary fog in the way that a chemical solution is different from clean water. The visibility in some areas reduced to less than 1 foot. Buses stopped in the road. Indoor performances at Smithfield were canceled because the fog entered through ventilation. People walking outside held one hand to a wall. The scale of what happened in those 4 days was not immediately understood. Deaths attributed to fog and cold in the first week were initially counted in hundreds, a figure not unusual for a severe winter period. The true picture took longer to emerge, worked out from mortality records in the weeks that followed by epidemiologists, comparing death rates against the same period in other years. The current estimate, produced by later research using improved statistical methods, places the death toll attributable to the smog at between 10,000 and 12,000 people, most of them elderly, or very young, or already living with respiratory illness. The account given here does not linger on that toll. It names it because it is the fact. But what the smog of December 1952 did to the legislative and regulatory landscape of industrialized cities is what carried forward from it most visibly. The Clean Air Act of 1956 in the United Kingdom was a direct outcome. It established smoke control areas in which the burning of certain fuels was restricted, required new industrial installations to meet emission standards, and gave local authorities the power to enforce those requirements. Other industrialized nations studied what London had documented, and in the following decades brought similar frameworks into law. The episode had a specific atmospheric cause, a temperature inversion trapping surface air long enough for accumulating combustion products to reach concentrations with measurable physiological effects, and the legislative response addressed that cause at its source, which was the uncontrolled release of combustion products into air that had nowhere to go. A temperature inversion is not an unusual event. It occurs on still, clear nights when the surface radiates heat upward and the air near the ground cools faster than the air above it. Valley floors experience inversions regularly. Low-lying basins in mountain terrain experience them frequently. The inversion that sat over London in December 1952 was not exceptional in its meteorological structure. What made it exceptional was the density of combustion it held in place, and the length of time the high-pressure system persisted without any wind to break the cap. By December 9th, the high-pressure system shifted. Wind returned. The inversion broke. The fog and smoke that had accumulated over 4 days began to disperse. Light returned to the streets. Thin winter light, the kind that arrives low and gray in London in December, not bright or warm, but light enough to see across a road again. The city resumed its visible shape. The inversion had done what inversions do. It had held the surface air in place while something accumulated inside it, and then when the conditions that created it relaxed, it released. The atmosphere moved back toward equilibrium. But what the inversion had made visible, in the most literal possible sense, visible as a wall of chemical fog, as stopped buses and closed theaters and 4 days without the ability to see the building across the street, was the relationship between what was put into the air and what the atmosphere could or could not carry away. The legislation that followed changed the air above London and, in a broader sense, over other cities in the industrialized world across the second half of the 20th century. Monitoring networks expanded, fuel standards changed, smoke control areas were extended and tightened. The particular episode of December 1952 became the documented case study behind decades of work on atmospheric chemistry, urban air quality, and the relationship between temperature inversions and the behavior of surface-level pollutants. Researchers have returned to it repeatedly, using it as a known documented event against which models of atmospheric chemistry and transport can be tested. Above the chemistry of the lower atmosphere, above the temperature inversions that hold surface air in basins and valleys, above the thunderstorm anvils and their upward electrical discharges, above the sprite-generating mesosphere and the ELV-producing ionosphere, the atmosphere continues. It thins, the pressure drops. The density of molecules decreases until the boundary with space becomes a matter of definition rather than a distinct line. But within the layers that are dense enough to count as sky, within the part of the atmosphere that interacts with light, that forms clouds, that holds moisture and conducts electricity, and traps the surface air on still December nights, there is more structure than most of what is seen from the surface suggests. A hiker on a Hards Mountain ridge in the morning fog sees a shadow in the cloud below and a ring of colors around it. A pilot above a polar region in winter sees stratospheric clouds glowing in colors that have no equivalent in ordinary weather, lit by a sun that has already gone below the horizon. A researcher at an altitude station captures by accident the first confirmed footage of something that has been happening above every thunderstorm for as long as thunderstorms have existed. A glider pilot in Queensland runs parallel to a cloud wall that is rotating along its own axis and stretching toward both horizons. A fire analyst watching pyrocumulonimbus from a distance describes the cloud as producing weather that has moved outside predictable modeling. Each of these is a different atmospheric phenomenon with its own physical mechanism and its own set of required conditions. None of them is particularly exotic in the sense of requiring the universe to behave unusually. They require only the ordinary physics of light and water, electricity and heat, pressure and temperature, combined in the specific ways the Earth's atmosphere tends to combine them when conditions align. The Brocken specter needs a ridge, a fog bank, sunlight from behind, and water droplets of uniform size. The morning glory needs two converging sea breezes, a shallow enclosed gulf, and a season when the temperature inversion at low altitude holds long enough for the Bohr wave to propagate. The Sprite needs a powerful thunderstorm and a clear path upward through the mesosphere. What holds these phenomena together is not their strangeness. It is that the sky, understood as a physical medium through which light and energy and pressure and moisture move continuously, turns out to contain more structures than the view from the ground shows. Looking up from the surface on an ordinary day, what is visible is weather, cloud, and blue, the occasional rainbow, the color of light near sunset. Below the surface of what is visible, and above it, and extending sideways in every direction, the same medium that produces that ordinary view is also forming nacreous clouds in winter darkness at 20 kilometers and expanding elf rings at 60 miles and rolling tube clouds over remote Australian shorelines and projecting shadows into mountain fog ringed with soft backscattered color. When the December fog finally cleared over London in 1952, what returned was ordinary winter light, pale, low, the kind that barely reaches into north-facing streets, but it reached. It came through the dispersing chemical fog and reached the surfaces beneath it, the stone of the buildings, the road pavement, the long gray river, in the same way that light has always reached surfaces in winter in northern cities, angled and thin and entirely sufficient. The air moved. The pressure system shifted. The inversion that had acted as a lid over the city for 4 days released its hold, and the surface air and what it contained moved outward and dispersed into the wider atmosphere, thinning as it went. The light came back through dispersing fog the way it always does, gradually, first as a difference in the quality of the gray, then as the outline of the building across the street, then as shapes in windows and the particular angles of London brick and stone becoming visible again at ordinary distances. The city went on, traffic moved, the river continued, and from that winter, from that particular episode of cold and coal smoke and the physics of temperature inversions, came decades of changed thinking about the relationship between what cities put into their air and what the air above them is able to carry away. That thinking is still in progress. The atmosphere is still the same atmosphere it was in December 1952, the same medium, the same physics, the same capacity to hold a surface layer in place under the right conditions. What changed was the understanding of what those conditions mean when they persist. On the evening of May 3rd, 1999, a research vehicle was parked on a road in central Oklahoma, its rear doors open, the instrument array inside humming against the steady ambient sound of the coming storm. The Doppler radar unit mounted in the truck bed was sending pulses outward into the air ahead of the approaching circulation, and the screen inside was returning a color gradient that the operator read once, then read again. The measurement was 302 miles per hour. Not across a broad swath of the system, not averaged across a long pass, but in a narrow band of low-level wind barely wider than a city block. The reading held for long enough to be logged. The tornado producing it was already on the ground near Bridge Creek, and the radar was close enough to resolve what the instruments showed at the scale of a street rather than a county. Wind speed at that level is measured in moments. The reading is a kind of photograph, a single cross-section of motion captured during the brief window in which a portable unit can sample it cleanly. What the Bridge Creek measurement showed was the interior of a circulation rotating at a rate that no instrument mounted to a fixed surface had previously confirmed near the ground. The velocity at that point in the vortex was more than 4 times what a strong sustained hurricane wind produces at landfall. It was a figure that, when the data was reviewed, required confirmation from the backup record before it was accepted. The outbreak that produced the Bridge Creek tornado generated 66 confirmed tornadoes over 2 days across Oklahoma and Kansas. That number, and the data collected during the event, shifted investment patterns in the Doppler warning network across the Central Plains in the years that followed. More radar installations meant more resolution. More resolution meant more warning time between detection and the moment a circulation reached the ground. The measurement on that screen in the back of a parked truck on a dusty Oklahoma road did not just record a record wind speed. It became part of the argument for building a denser, more redundant version of the system that had produced it. The color on that radar return was a narrow stripe on a scale the operators had calibrated, but rarely seen, pushed that far. The numbers attached to those colors were not dramatic in themselves. They were the output of an instrument doing what it was built to do. The tornado continued its path. The vehicle moved. The data was saved. There is a particular quality to wind records taken this way, with portable instruments in the field during active events, in that they represent a single point in space, during a single passage of an event that is itself always in motion. The 302 miles per hour reading belongs to a moment that lasted seconds. The tornado existed for longer. The storm system existed for days. But the number that came from that evening belongs to those few seconds of radar return, logged to a printout, stored in a research archive in Norman, Oklahoma, where it has remained for 25 years as the highest wind speed ever recorded near Earth's surface at the time of its measurement. What the Central Plains produce in spring and early summer has to do with the geography of the continent, with the dry air moving east from the Rockies at altitude, and the warm, moisture-laden air pushing north from the Gulf of Mexico at the surface, the two systems meeting over flat land, with no topographic barrier to interrupt the shear between them. The terrain is broad and low and open. Visibility extends for tens of miles on clear days. On storm days, the anvils of supercell thunderstorms are visible from 60 or 80 miles away, their flat tops shearing eastward in the upper winds, while the base rotates slowly below them. The flatness of the land is part of what makes the storms visible. It is also part of what makes them possible. A haboob is a different kind of wind entirely, not rotational, not drawn from the meeting of two colliding air masses, but the forward edge of something collapsing. When a thunderstorm's downdraft reaches the ground and spreads outward faster than the storm itself is moving, it pushes ahead of the rain like a wall rolled forward by the system's own weight. In dry country with loose surface soil, the outflow picks up what is on the ground and carries it. The word itself is Arabic, from a root meaning wind, and the storms it names have moved across desert terrain in the Middle East, Northern Africa, and the American Southwest for as long as those regions have been dry enough and loose enough to produce them. In July of 2011, a haboob formed ahead of a collapsing thunderstorm complex west of Phoenix, Arizona, and moved east across the desert floor toward the city. It was estimated at 100 miles wide and approximately 5,000 feet tall, a wall of suspended dust advancing at roughly 60 miles per hour across ground that had not seen significant rain in weeks. From the eastern side of the city, the structure was visible from far out. The horizon to the west simply filled in, the brown mass coming forward at a pace fast enough to see in real time, and the Phoenix skyline, building by building, disappeared behind it. The leading edge was defined and solid, the way a weather front can appear from a distance before the eye understands its scale. 5,000 feet is the height of a small mountain. The haboob that moved through Phoenix that evening carried that height forward at highway speeds across open desert. The material suspended in it was fine enough to work through window seals and settle on indoor surfaces. The advance was visible from space in satellite imagery taken that evening, a distinct brown lobe moving into the urban grid of the city. By the time it passed, the temperature had dropped by several degrees, and the air had the particular flatness of a space that has just been rearranged. The physics of a haboob are entirely contained in the mechanics of the downdraft that produces it. There is no rotation, no funnel, no sustained organized circulation. The air simply falls from altitude, strikes the ground, and spreads outward. In humid country, that spreading air produces rain and briefly gusty conditions that most observers would experience as a storm passing. In desert country, where the lowest layer of air is too dry to sustain the raindrops that fall through it, the rain evaporates before it reaches the ground, and the cold air arrives first, alone, carrying whatever was loose on the surface. The haboob is in this sense the signature of evaporation, the mark left by rain that never landed. The mistral is older in human knowledge than the instrument record of it. Provençal farmers knew it as a persistent fact of their landscape long before anyone had a word for the pressure gradient that drives it. It comes down through the Rhone corridor from the north and northwest, channeled by the Alps to the east and the massive central to the west, into a narrowing passage that accelerates it, the way a river accelerates in a canyon. By the time it reaches the open coastal land south of Avignon, it is moving at sustained speeds between 45 and 90 miles per hour, cold and dry and steady, sometimes for days at a time. The buildings that have stood in the Rhone corridor for centuries show the Mistral in their construction in a way that no written record needs to explain. The north face of the traditional farmhouse is solid and without windows, the walls thick, the roof line asymmetric, with the slope toward the north steeper and lower than on the south side. The cypress trees planted along the northern boundaries of properties are tall and narrow, and each one leans almost imperceptibly toward the south, bent by the accumulated pressure of decades of wind coming from the same direction across every growing season of their life. The farmhouse and the cypress tree are both instruments in a sense. They are physical records of a wind that has been arriving from the same direction for as long as the land has been cultivated. The mistral does things to the air that the region's agriculture depends on. It drives the humidity down and keeps the canopy of olive and grape dry, through periods when morning dew and coastal moisture would otherwise hold enough water to allow mildew to establish itself in the crop. The wind clears the air in a literal and measurable sense, dropping particulate matter and humidity in a matter of hours and producing the quality of light that painters have described over centuries as distinct to Provence, a clarity with no softness in it, the shadows sharp-edged, and the colors of stone and earth fully saturated. That quality of light is in part the mistral doing what it always does. The same wind that shaped the farmhouse and bent the cypress tree and kept the grapes dry enough to harvest was named in Roman times and has been a subject of legal and agricultural dispute in the region for centuries. There are historical records of Provençal courts arbitrating cases in which the mistral was invoked as the cause of property damage, crop loss, and injury to workers in the field. The wind was a legal presence before it was a meteorological one. It has been blowing down the Rhone toward the sea since before those records existed, and it will continue after the last of them is stored in an archive. A derecho is a word most people have not encountered, and the storms that carry the name are easy to misidentify in the absence of the label because their defining characteristic, straight line wind rather than rotation, makes them look in their damage pattern like the remnant of something that passed rather than something that arrived whole and organized. The word was coined in 1888 by Gustavus Hinrichs, a meteorologist working in Iowa who needed a term to distinguish the straightforward character of this type of windstorm from the rotation implied by the word tornado, which derived from the Spanish for thunder and carried the sense of turning. Hinrichs chose the Spanish word for straight or right, and the name has remained. To qualify as a derecho by current meteorological definition, a convective windstorm must travel at least 240 miles and maintain damaging wind speeds across that distance. The system is not a single cell, but a line or cluster of convective storms that organize and reinforce one another, the leading edge of the complex, driven forward by the outflow of cold air from the storm's combined downdrafts. Where a supercell tornado touches down and traces a path measured in miles before lifting, a derecho traces a path measured in hundreds of miles and can take hours to pass a single point on the ground. On June 29, 2012, a derecho formed over Indiana in the late afternoon and moved east along a track that carried it across Ohio, West Virginia, Maryland, and into the mid-Atlantic coast region by early morning on June 30th. The system covered approximately 700 miles in under 12 hours. The winds ahead of the leading edge bent and snapped trees in the darkness as the system moved through populated areas during the night hours. By the time the complex weakened over the Atlantic coast the following morning, more than 4 million customers in the affected region were without power. The path of the storm could be read in the utility outage map as cleanly as a radar track, a long east-moving band of disruption drawn across several states by a system that had traveled the length of the corridor in a single night's motion. The June 2012 derecho was not unusual in structure, only in scale and timing. Derecho events occur several times per year across the central and eastern United States during the warm season, some tracking south, some east, some dissipating before they reach their definitional minimum distance. What made the 2012 event notable was the combination of its length, its overnight arrival in densely populated areas, and the depth of summer heat that had preceded it, and had loaded the atmosphere with the instability a convective line needs to sustain itself across that kind of distance. The heat had set conditions. The derecho read them. A line of thunderstorms traveling at 60 miles per hour in darkness produces a particular quality of arrival. There is no visual warning except the occasional illumination of the clouds themselves by the lightning they carry. The sound of wind in trees rises before any rainfall arrives, and the rain, when it comes hard and fast. The whole system moves through a given location in minutes. The before and after are clear sky and branches down, with the passage itself brief and loud, and then completely gone. The storm already 100 miles to the east by the time the first assessment begins. The roaring 40s begin where the land runs out. Between 40 and 50 degrees south latitude, the continents have narrowed and separated enough, that the Southern Ocean wraps around the globe in a nearly unbroken ring, and the westerly winds that flow through those latitudes encounter almost no frictional resistance from terrain. They circle. They have been circling for as long as the continents have held their present positions, which is tens of millions of years. There is no beginning and no end to the circuit, because the circuit has no interruption. Navigators who reached these waters in the 17th century were working with the physical evidence available to them, which was the behavior of their vessels and the pattern of swells they found when they crossed below the southern tips of Africa and South America. The Roaring Forties were not a discovery in the sense of finding something previously unknown. They were a recognition, the naming of a pattern that had always been there, expressed in the movement of the water and the behavior of the wind against a sail. Once identified, they became a route. Navigators bound east from Europe toward India or Australia could drop south into those latitudes and let the westerlies carry them at speeds not achievable in the calmer zones further north, shaving weeks from the passage. The clipper ships of the mid-19th century were designed with those latitudes in mind. Their hull forms and rigging configurations were optimized for running before a strong following wind, and the routes they sailed kept them in the Roaring Forties across the longest available stretch of the Southern Ocean. The crews worked on decks that stayed wet for days at a time. The swells in those latitudes are long and large, generated by thousands of miles of uninterrupted fetch, and the ships moved through them with the particular motion of a vessel, running downwind in heavy seas, the hull lifting on the faces of waves and sliding down into the troughs in a rhythm that repeated without variation across days and weeks. The land they had left fell astern quickly. The land they were headed toward remained beyond the horizon for weeks. In between was wind and water and the continuous westerly push. The zones further south than the Roaring Forties earned names that reflected the character of the winds that navigators found there. The belt between 50 and 60 degrees south became the Furious Fifties. The band approaching 60 degrees and below became the Screaming Sixties, closer to the Antarctic continent, colder, the seas steeper, because the water depth decreases as the seafloor rises toward the ice shelves and the swells pile up rather than running long. These were names given by the people who sailed through them, not by cartographers. They described the physical experience of passage, the quality of the wind as it entered the rigging, and the character of the water in those latitudes, and they passed into use as practical navigational shorthand for anyone planning a voyage that far south. Today, the Roaring Forties are crossed regularly by cargo ships and sailing vessels, and the westerlies that drive them are measured by satellites and modeled in forecast systems. The physical mechanism has been understood for a long time now. A persistent pressure differential between a high-pressure belt at about 30 degrees south and a deep low-pressure trough near the Antarctic continent drives air consistently from west to east, reinforced by the absence of any land to create drag, sustained by the temperature contrast between the mid-latitudes and the polar region. The math is clean. The phenomenon it describes is a river of air, hundreds of miles wide and thousands of miles long, circling a planet continuously in both hemispheres, its southern branch uninterrupted, its northern branch fragmented by the presence of Asia and North America and Europe sitting across its path. The Southern Ocean westerlies carry moisture, they carry energy. In the right conditions, where they interact with the land at the southern tips of the continents, they deliver weather systems in rapid succession, one after the next, the interval between fronts sometimes measured in hours. The western coasts of southern Chile and the southern tip of New Zealand receive among the highest annual rainfall totals in the world because of what the westerlies carry in from the ocean. The moisture they hold accumulated across thousands of miles of open water, where evaporation from the surface loads the air with water vapor that eventually reaches the land. The mountains intercept it. The rain falls. From high enough above, the pattern of the westerlies in the Southern Ocean looks like what it is, a band of motion around a sphere, consistent in its direction, variable in its intensity, but persistent in both. Weather satellites passing over those latitudes in polar orbit cross the westerly belt twice per pass, and the images they return show the spiral cloud bands of frontal systems embedded in the general westward to east flow, each one tracking the same direction as the one before it and the one after, the whole system in a state of continuous organized motion across an ocean that has no eastern edge, only a continuous surface. There is something in the physics of the Roaring Forties that has no tidy comparison in everyday experience. Most winds that people encounter have a source and a destination. The sea breeze comes from the water and arrives at the shore. The mountain wind comes down from the ridge and settles in the valley. The mistral comes from the north and ends at the Mediterranean. These are winds with a geography, a from and a to. The Southern Ocean westerlies have no such structure. They do not come from anywhere, and they do not go anywhere. They simply circle, driven by a temperature differential and freed from interruption, the same motion repeated across the same track, across the same latitudes, year after year, and decade after decade, and longer than any recorded human presence on the planet. The ships that used these winds understood them as a resource, something to be entered and exited at the right moments, like a current in a river. A captain heading east from Cape Town toward Australia would ease the vessel southward until the westerlies filled the sails, run with them for as long as the route required, then ease north again toward calmer water as the destination approached. The Roaring Forties were not a destination. They were a medium, a band of motion that could be borrowed temporarily by anyone willing to enter them and capable of managing what they would find there. What the Southern Ocean looks like at night in those latitudes is something that requires a particular kind of darkness to appreciate. The nearest land is hundreds of miles north. The ice edge of Antarctica is hundreds of miles south. There is nothing in any direction except water and sky, and on a clear night, the sky in those latitudes holds more stars than are visible from most inhabited places on Earth, because the air is clean and the horizon is wide, and there is no light source within any useful radius.